Howdy and welcome back. So we're going to continue our discussion by discussing a couple of basic types of graphs along with some select properties thereof. So the first type of graph that I'd like to introduce is going to be an undirected graph. The mantra of this graph is going to be that its edges are bidirectional and you can move, say, from one node x1 to x2 and back across the same edge from x2 to x1. You can think about this as maybe a two-lane highway where you're free to move from the source to the destination and back along the same kind of roadway here. Contrast this with directed graphs, which are shown on the right. Notice here that we don't have that just line between, we have a line with an arrow, which is implying some sort of directionality. What this means is that there is a true source from which we can walk to, say, a destination vertex. So in this case, along the edge x1 and x2, we can only move from the source x1 to the destination. There is directionality enforced here, and you can think about this edge as a one-way street. We can only move from x1 to x2, and notice that we could only move back to x1 from x2 had there been a directed edge from, let me do this in a different color, from x2 to x1. But that edge does not exist in this diagram, which means from x1, we can only move to x2 or x3. From x2, if we look at its edges, outward edges, so those departing from x2, we can see that we can only move to x5. So this is kind of the key difference between a undirected graph where the edges are literally undirected, contrasted with a directed edge where there is that directionality that is enforced by the edge. There's that it's that one-way street kind of analogy versus the undirected graph where we have that two-way street and thus flow of information. Now, continuing on, there is going to be this idea of a simple graph and then on a multigraph. Well, what are the differences between those? In a simple graph, each edge is going to connect two different vertices. No two edges are going to connect the same pair of their vertices. So if a relationship exists between x1 and x2, that is going to be communicated through a single edge in a simple graph. We would not have the ability to have, say, multiple edges connecting those two vertices because by definition, we're going to see here that's a multigraph and not a simple graph. So simple graph, each edge connects two different vertices. No two edges connect the same pair. Multigraph, more than one edge can connect the same pair of vertices. And we'll see there's some implications for this when we start talking about the applications of our graphs. In this case, though, we can see that the example on the right is a multigraph just based on the fact that we have two edges connecting x1 and x2. We have this one here as well as this one here. So let's think about that a little bit and continue on with our discussion here. So loops and cycles. It's going to be kind of a similar idea, though it's going to be defined differently. So a loop is going to be an edge that connects a vertex to itself. So it's just where the source and the destination are the same. So that's this example here. Notice that this edge is effectively x1, x1. It's connecting to itself. Now a cycle is going to have a more involved kind of definition here than this idea of self-connection. A cycle we're going to define here is going to be to simply a little bit of hand wavy to kind of stray away from the mathematical definition of this. And we're just going to say that there exists a circular path back to some starting node. And we're going to say that in a simple graph, such pathway must have at least three vertices involved in it. So if we go ahead and look at this example here, we can see a cycle come out. We can see that x1 is connected to x2, which is connected to x3, and now finishing the cycle, so connecting us back to our starting point, is going to be this connection between x3 and x1. Now, another kind of important property that might be of some benefit later on is going to be the degree of a vertex. This is going to have a definition depending on the sort of graph that you're working with. In an undirected graph, the degree of a vertex is going to be the number of edges incident to the vertex with a loop contributing to the degree of that vertex. So if we look at x2, the degree of x2 would be, well, how many edges are incident to it? 1 and 2. So it will have, whoops, a degree of 2. Now, in a directed graph, we're going to focus on the directionality of it. We're going to say that the end degree is going to be the number of edges that terminate at a particular vertex. So in the case of x2 here, the end degree, we see one edge terminating there. It's that originating from x1. So x2's end degree would be 1. And then we'll go ahead and define the out degree as the number of edges that begin from that vertex. So in the case of x2, we see a single outbound edge that is moving from x2 to x5. So we would say that the out degree in this case is going to be 1 as well. We have one edge coming inbound, one edge going outbound. So there we go. So we've kind of gone through, okay, we have this idea of a graph. There's these different types of graphs. There's different attributes of the graphs. Well, how do graphs prove useful? And we'll see that they are very helpful in establishing relationships between the various entities comprising the vertices set.